So today we're going to present distributed principles in a cloud-native database. This is a topic that I love. I love all the topics we typically talk about on our webinars, but this is something that I have been into for a couple of years now. In fact, going way back to when I very first met our CEO, Spencer Kimball, and just kind of to look at distributed principles and how they apply in other systems, I think is hopefully is interesting and compelling for all of you. And you get some value out of this as well, is learning a little bit about Cockroach. But a bit of housekeeping first. A recording definitely will be available after the event. Everybody asked that, so we'll put it up. It'll be on our YouTube channel fairly quickly, actually. I think we're doing both Zoom and a YouTube stream for this, so I think the YouTube stream will be up there pretty quick. Please do ask questions in the QA panel and engage us in the chat. My friend and an incredible sales engineer of ours, Michael Goddard, who has some really deep expertise in this area as well, been with us for a while now, is ready and willing to type until his fingers fall off if need be. Sorry, Michael, I will try to cover everything, but so please do engage us in the QA and the chat. We'll definitely answer those things. I'll try to monitor it along the way as well, so that I can insert some questions into the talk track. But we've got a lot to cover today. It should be a full hour of content here. So today is definitely it's intermediate, and I would say actually intermediate to advanced. We are going to talk about some of the internals of Cockroach database and how we built it. We're going to talk about replication. We're going to talk about Raft, distributed consensus, how we do distributed transactions, latency, the speed of light in distributed systems, and its impact, and then some of the things that you can do within a particular instance or a node to actually break down and attack the problem of latencies and round trip time between places and all this stuff. And so this session will be fairly advanced. So I call it intermediate because, hey, I'm a marketer. But I live and love getting into the deeper layers of this tech stack in particular, because I think I've learned a lot myself in terms of how distributed systems work. And I hope this conversation, like I said at the very top there, will not only give you some insight into CockroachDB, of course, and Cockroach database, but also some of the principles that we used. And I think there's a lot of learning and a lot of stuff that can be taken away from some of the stuff that we've built that may help you in building your own distributed systems. And as you kind of move to these kind of microservices and whatnot, and some of the things you need to be concerned about. That said, we are an open source company, so our code base is actually open as well. So if you see something here that was interest to you, go inspect it. Go learn how we coded it. It's all in Golang, so if you know Golang, it's pretty easy, but pretty simple language to learn and kind of follow. So I will give you that, and then before I make a commercial for our docs, because I'm going to do it at some point during this webinar, our docs do a pretty good job of describing everything that I'm going to talk about now. Is well outlined in our documentation. So again, engage us. We're happy to take questions, and I will, like I said, try to look at the QA and chat along the way. So I start with this concept of cloud database because the cloud is interesting because I think every organization on the planet looks to kind of move to the cloud, but and we think about the cloud as like this new way of thinking about infrastructure. And I used to work in an office where we had a room where there were a bunch of servers in it. That's just not even a thing anymore. But I argue that infrastructure and the surface area between infrastructure and applications is really that database. Now, there's lots of options for database in the cloud, right? We could take a legacy database, deploy it in the cloud. This is, running MySQL, an RDS instance of MySQL, something like that, right? Running Oracle in the cloud, right? This sort of thing. So you kind of lift and shift the traditional database. Now, these things are interesting. They work. They work for some of our applications. They don't deliver on the full value of the cloud, the elastic nature of how do you scale that thing. You're still scaling on a single instance and saying, hey, look, let me get a bigger machine, a larger instance, right? And so you're still kind of only vertical scale. Now, some things have come about that help us with kind of more horizontal scale. Aurora is one of these things where they took like a layer of the architecture and changed it, the storage layer, made that distributed. They're augmenting some of these legacy technologies to make them kind of cloud ready and make them more cloud databases. Also interesting stuff and great solutions. This category of technology that I'm going to talk through today and kind of some of the principles that are here was really led by kind of the work that was done at Google with Spanner. And there's a white paper The Google Cloud Spanner white paper is a phenomenal read, and I think a baseline read in terms of how distributed systems kind of work. CockroachDB is actually built a lot off of that paper, and we share a lot of the same common core principles. I always contend that if you're building distributed systems, moving towards these kind of cloud native architectures, looking at what Google has done over the last 15 years is really fantastic. So, but today, my familiarity is definitely with CockroachDB and our approach to actually delivering this kind of distributed SQL, which really is kind of a new breed of database where it is kind of re-architected to be fully distributed. And if you're going to be a database, well, I just find for relational databases for sure, SQL is a requirement. And ACID transactions, being able to scale, I think, is a core principle and a core primitive of distributed systems. I think designing systems for resilience and being able to survive failures. Also a core primitive of distributed systems. Always on and resilient, having data available and low latency access to data, I think, is another key piece of being a distributed system. As you have compute that's spread out over the whole planet, how do different instances of the same compute communicate? How do you deal with ultimately what is the speed of light? At Cockroach, what we're doing is we're tying data to a location. We built that into the database itself. But a key concept, especially as we start thinking about distributed systems in global scale, it's important in a single data center as well. But I think ultimately at global scale, these things become extremely important, right? So, all right, so let me, all right, so let's get into this. So CockroachDB, again, architected for the cloud. This is a relational database. It implements familiar standard SQL. We're wire compatible with Postgres. In order to scale, Cockroach is implemented as a series of nodes that all kind of intercommunicate with each other. You simply spin up an instance and point it at the database, and the database will actually rebalance all the data across these nodes, so you can either on maybe even utilization, even storage. And we're going to show exactly how we actually do that. But ultimately, this is one single logical database. You can ask a query of any single node. So just put a load balancer in front of this, and you're going to be able to find the data no matter where it lives across all these different nodes. And we can scale even not just within a single data center, but we can actually scale across regions. So now you have one single logical database spanning an entire country or the planet, if you will. And if you really wanted to expand that out, is a region a cluster? Is a region a cloud? We can actually span a single logical database across, multiple different cloud providers. I like to think about this as multiple different Kubernetes clusters as well. I'm a Kubernetes freak, so we can do that as well. And so, how do you federate data across different environments? I think is a really key piece of our architecture. We're going to show you how we do that. Tying data to location in these kind of situations, these architectures becomes very, very important because you don't want to deal with egress costs, this sort of stuff, right? So, and we'll show you how to do that. Cockroach is also naturally resilient. If a node fails, a rack, a server, an entire AZ, an entire region, an entire Kubernetes cluster, it's resilient enough. And depending on how you place that data in the cluster, you can survive that failure without any impact to your transactional load. So all reads and writes are still being serviced, and say, whatever your SLA is, whatever your P99 latency you're looking for, is it 10 milliseconds? Is it 50 milliseconds? All tunable, and you'll see a very limited impact into transactional volume, and more importantly, the performance that you're actually meeting the needs of these applications. It's just always on, right? We distribute data throughout the cluster in a very intelligent way. I'm going to show you through that. One thing that's actually pretty important, though, in Cockroach, like I said this before, any node can service a read or a write. So I don't have different types of nodes. I can ask anything. So typically what we see is people will set up a load balancer in front of each region to actually balance load across, how many nodes there are. But data can actually be located, and we could tie data to particular locations based on how we name each node. So in this case, you could see there's 3 records here: Kimball, Madison, Stewart. 2, like those records, some of them are in the US East. I have 2 instances of that. We're actually writing data in triplicate in say European cluster. But I know I want that person is in Europe. So if I ask a node that's on the West Coast, Cockroach is smart enough to go get that data from where it needs to get it from. We do this because, well, this user is actually Kimball. They want their data, and they're in Europe all the time. So we can locate data close to that user to really reduce these read-write latencies. And that's kind of a unique thing of what we're doing. But again, I think a core principle and a core concept and understanding of distributed systems in terms of dealing with latencies, how do you tie data to a location and make sure that we are meeting these latency requirements of our applications, right? So that's CockroachDB in kind of a nutshell in terms of some of the high-level things that we can do. The database is available to you, open source. Our core version implements all of this stuff. We have an enterprise version, tacks on a couple of features. I'll go through that in a little bit, but Cockroach Cloud is available for a 30-day trial, full version of the software. And then we also have Cockroach Cloud Free, which is a free version of this, something that we're working on to make it, forever free. You can spin up a cluster and you're going to have access to this data all over the planet. And so that's all available. Cockroach also delivers all the integration, the management. We built a cost-based optimizer, all the security constructs that you need, all there. But most importantly, I think the very last line here, documentation. I think we have some really world-class documentation. Again, everything I'm going to talk about here, you can go check out in our docs. So, all right, so let's get into the architecture. Let's get into the meat of this conversation. So, all right, I've only wasted, 10 minutes of your time going through the high level of Cockroach. Let's get deep into the weeds of some of the architectural things. So real quickly, somebody was just asking the QA, does the community version support geospatial data types? Absolutely. We just released geospatial as a huge increase to our entire code base. So all the geospatial capabilities were released into the open source core version of our software in our 20.2 release, which I believe was last October. So definitely available. And thank you for the question. See, I am trying to monitor at the same time. So, okay, so at the core of Cockroach, at the core of us as a distributed system, ultimately, we're storing data. We're storing tables of data. And here's a table. It's the dogs table. I've broken it down to the simple, like here's the keys basically for that table. And what you're seeing is an alphabetical list of dog names. And so there probably is a bunch of other information, the sex of the dog, the weight, its age, right? There's probably a bunch of things, right? But basically, if you look at the key space on each one of these tables, it's basically an ordered lexicographical sort, right? And so this allows us to do some really cool things, right? And so ultimately, let's start there. Oops, I'm going the wrong way here on my slides, excuse me. But in a traditional database, the way that we would store data, you would have, say, an inventory table, and you would just keep appending records to this table. And typically the way these things get written is, you just keep appending storage, storage, keep going down. And then you would have an index that allows you to access this data very quickly with pointers to some memory space. So you can actually do some other things, right? You do some primary indexes, and secondary indexes allow you to do some really interesting things. And this is the relational form that's been with us since System R in 1972, way back in the day, right? And so this stuff is works. And the relational approach to data, the way that we actually interact with this stuff is all via SQL. And I believe they still teach this at university. I learned it, but ultimately this doesn't work, from a distributed system point of view for several different ways, right? Now, what we've done is we're actually using KV as the backend store, right? Whereas relational is just kind of appending and doing these things. We're actually using KV because it gives us this kind of a very efficient method of storing and distributing data. It allows us to kind of break off, ranges of data into these chunks that allows us to do some really cool things around how we distribute data. But we also get kind of some really powerful value from the value of a KV store, right? I can do these really efficient range scans, getting a key, putting a key, these values. We can get really efficient on where that happens within a cluster. And that's really important because in a distributed system, you want to be concerned about not just the logical data, but the physical storage of that data itself. And so if you know exactly where geographically something is going to be in the cluster, really, really important. And we'll come back to that, right? Now, in Cockroach, it's important to note, again, all the tabular data is stored, this monolithic sorted map. All tables have a primary key, and that key is used really as the K in the KV store. And we're going to actually append a lot of things. We're going to actually compile a lot of things into what that primary key is. Now, there's a great blog post on choosing a primary key for CockroachDB. That's on our blog roll somewhere. but it really helps you kind of understand this thing. Now, to me, this was when I really started to understand Cockroach, was really understanding at the storage layer how all this stuff came together. But let me explain how we actually can translate something that looks relational into KV. So here's a table. Here's the dogs table. ID, name, and weight. There's my simple statement to create the table. And there is some sample entries, right? So that I'm using ID 347A. So it looks like some hex code to actually say, hey, here's some records. Here's 4 records that I want to write. Now, these 4 records, when they actually get stored to disk, are broken down into basically the key and then the values for each of the columns, right? And so the key is, it's the dog table, and the key is, well, the ID 34, and then the column name is name, and under that name is Carl. So the KV here is basically the table, the ID, the key value for that relational table, and the column all appended together. And then we're going to encode this into some really interesting things, underneath the covers. It isn't going to look like dog 34 name. It's going to look like hex code. Hex code allows us to do some really cool things, right? And then we're going to store a value. And we do this for each row. But what you're seeing here then is basically this lexicographic sort of all of the values for all of these keys. Now, imagine in a table with thousands and thousands and thousands of rows, how this actually spans out. Now, it allows us to do some really cool things, but understanding this is kind of part and parcel to understanding Cockroach, right? We're going to be able to sort some things really interesting. We're going to actually ensure against null values with this. And most importantly, we're going to actually maintain integrity. But the sort is really what allows us to do some really cool things. So let's come back. We have this monolithic key source. Now, what we do is we break each table, this lexicographically sorted table, down into ranges. Now, a range is a shard or a tablet. I think you'll hear some databases call this, right? And so what we're doing is we're just basically automatically taking a table and breaking it down into a size of 256 megabyte ranges. Now, we chose this because it allows us to kind of move things around and split things. And I'm going to show you how we split. And then it also kind of allows us to really optimize the way that we're indexing on top of this. We have to index because we have to actually understand where this data is living. And if you're going to write to this table, well, you need to know which range. Basically, you don't have to shard anymore. We've taken care of it for you. And this is all completely automated, right? If you're going to automatically do this, well, we actually create an index structure to understand where each one of these ranges are going to be. So this works very much like a B tree. So if you've ever actually coded B tree, it's pretty simple and straightforward. So it's pretty simple to understand. But again, this allows us to do some cool things like some very efficient range scans, right? So I don't have to go get every single range and pull it together and then do a scan. No, I'm just going to get the ranges I need to do a range scan, which is actually fairly efficient as well. I want to make sure I'm on time here. So we're doing well here. All right. So what happens when I want to insert a record into this table? I'm going to insert a new dog named Sunny. That's my friend Jeremy's dog, actually. And I'm going to go through that index. And I know that this is in the 3rd range. And that 3rd range is, I believe, red. I'm a little colorblind. And I'm going to insert Sunny. Now, is there space available? Well, it looks like it. Yeah, there looks like there's one space. So great. Insert that record and return acknowledgement. Great. We've now inserted that record. Okay, now I want to insert another dog. I want to insert Rudy into this table. Well, this range is full, right? I don't have space here, right? Because I just added Sunny, right? And so what happens is underneath the covers, Cockroach is going to take that range and automatically split it. And a new range index is created and we maintain order. So now I have space to insert this record and I insert it and everything looks great. Now, we aren't doing this in real time. I think the real time would actually add some latency to a transaction. So we're actually able to, kind of control when this happens, basically, when a range is dormant, if you will, we automatically will split the range. We'll go through and look at the database and look at the storage and say, okay, what needs to be kind of cleaned up here? And so, we'll do this in kind of the background, if you will, to make sure that this isn't going to affect anything because I've got to actually, hold off these 2 ranges and split them and then bring them back online and make sure the index is up to date, right? And so we're going to do that also kind of in the background, right? And so that's the very first concept that I wanted to walk through. I've got a couple more to go through, all of them equally as important, but how ranges work and how we're actually able to take, KV and map that to relational is really critical to understanding Cockroach and how we actually implement this as a truly, transactional relational database. Because ultimately, you're just saying insert, record into table, and we're taking care of all this in the background. And this magic is really what allows us to do some really interesting things around how we scale and then how we actually deliver this resilient form. I think from a distributed principles point of view, though, it's important to think about like chunks of data and chunks of compute that you want to actually take care of, and how you're going to manage that in the system. And how we manage that in the system is really, there's a concept called Raft. All right, so so there actually is a really good question. Thank you, Reddit. How do you avoid hotspots, i.e. all records start with a prefix AAAA? So we get this a lot. So a lot of people, when they create indexes on the table, they'll just do a count. 0001, 0002, 0003, 0004, right? Like they just do this incremental count. And when you actually implement a distributed database like ours, you can still use that as, say, a key within the table, but we recommend that you use things like a UUID, or you compile that with something else and do something a bit more random, because you do want random distribution, or do you? And it really depends on what you're trying to accomplish, right? Because we do want to avoid hotspots, right? Because if you did have these like sequences, well, then it's just going to be that last range is always going to be split. You don't want to do that, right? You want to actually effectively think about how the data is being stored. And I think, it's a great question, because I think one of the most important things to think about, there's a lot of value in a distributed database, automating scale, being always on, being resilient, being able to tie data to a location and affect how quickly people get. I think there's a lot of stuff that's really cool, but you got to think about where data lives. And so we're not just thinking about the logical database anymore and tables. You have to start to think about the physical database as well. We had a webinar with DoorDash, and Sean from DoorDash was on, and we were asking him some of the things that you got to think about differently. And he gave us an example that I think is actually pretty interesting. As a developer, we think about an insert into a table as like, I'm going to insert these 1,000 records into, insert 1,000 customer names into customer table. We're going to run that as kind of one query, right? And it's one insert statement. By default, it's like, yeah, run that against one machine. And in a vertical kind of scale up box, yeah, the box is going to be able to handle that. Well, in a distributed database, you want to start thinking about that as like, maybe it's 100 insert statements across 100 nodes, right? Because you get this more efficient use of compute. And, there's a different execution, different distribution of that data. And so there is this kind of like mental shift. And that's why I'm very happy, this webinar is about distributed principles and distributed concepts. That's the kind of distributed concept that I think becomes really important as you start to build out distributed systems. Like distributed thinking is one of those things that I think are definitely interesting. So there was a follow-up question about time series and whatnot. Would you use distributed SQL for a time series implementation? I think it depends on what you're trying to do. There's a lot of, time series databases, Timescale, my friends over there, Influx, you can use the right tool for the right thing. Typically, time series database is kind of an operational thing, or, you're looking at like maybe a Prometheus endpoint, like maybe yours in Prometheus, right? And so certain databases are built for different things. This is definitely relational, transactional workloads, less about kind of analysis of time series data. And we aren't optimized for that, honestly. We're optimized for transactions. And we're going to talk about transactions in depth here as well. But again, I think it really comes down to what you want to solve for with your particular workload. And that's kind of how these things come together. So, okay, great. Let me check. Okay, great. Time check. We are on track. So Raft is a distributed consensus protocol. And if you're not familiar with distributed principles, I would suggest starting here. I think Raft is such a great baseline for people to actually understand really distributed principles. If you look at like etcd, which is a core part of Kubernetes, implements Raft. I believe Vault from our friends over at HashiCorp. I think it's Raft, but definitely have a distributed consensus protocol, right? There's layers of distributed consensus that are happening in these distributed instances, and a lot of it starts with Raft. And so Raft is just a way of thinking about data in a distributed form and gaining consensus about what is the right set of data in that, right? And so In Raft, basically, what we think of is a Raft group. And one replica of a range is selected as a leaseholder. But if you look at on the chart here, we have the blue range that I had. What we're doing is we're writing data in triplicate. So there's 3 copies. Our Raft group is our replication factor is 3. Now, one of those copies is actually more important than the others. It's the leaseholder. It has basically, it coordinates what's going to happen across the triplicate, across what's going to happen in this Raft group, and it's going to be kind of the authoritative, up-to-date version of what's right. It's kind of going to be like it's going to be the leader, if you will, right? Now, when we write data, commands are really proposed to the leaseholder, and then it basically then drives how transactions are going to happen. I'm going to walk through an example of that in a little bit. Now, each range is a Raft group. We're going to default to 3 replicas. It is configurable. You can have a Raft group of, say, 5 replicas or 7. Odd number, because we're going to do something called a quorum write. 2 of 3 nodes need to commit before I can actually say something has committed, right? We need a quorum, right? This is a really chatty protocol. If you think about this, this was a range of, what I had 5 records. What if I had 8 million dogs in this thing? There are a lot, thousands, hundreds of thousands of ranges in a cluster, all managed by the backend database, hundreds of thousands of shards, all being managed and split and collapsed and moved around all intelligently by the database, okay? So Raft is really critical. Now, how do we distribute this data? Where we place records in a cluster, physically in nodes in the cluster, really depends on different things and different heuristics that we can actually go to, and really controllable by whoever's actually implementing and operating the database. But we can do lots of different things in how we actually do these things. I think of this as diversity in how we're actually placing data, right? We could survive, or we go do it by disk, a single machine, a rack, a data center, a region, a Kubernetes cluster. These things can all be kind of failure domains. What do you want to survive? And so if you look at this table, we had our 3 ranges, right? This is the lexicographically sorted. Now I have it by color. And so if you take the first range, we're going to actually evenly distribute this across the cluster. So Cockroach is smart enough to just say, okay, right, I need to write 3 copies. I have 4 nodes, write 3 copies on 3 nodes. I take the blue range, I take the red range, and now I have actually written this data to a cluster, and I evenly distributed this across the cluster based on basically storage, right? Like how full each of these nodes are going to be. We can also do something very interesting in Cockroach and actually balance things based on load. And we're actually always taking heuristics about load across a particular range. So if you do have that hot range, Cockroach is smart enough to say, hey, let's isolate that range into one of the nodes that has, by itself. So it isn't basically overtaking the compute. And that's one way in which we will not just optimize based on storage, but optimize based on kind of utilization and load that's happening on a particular box, right? But we can. I think this was a copy. Yeah, there was a copy of. Oops, sorry, y'all. I went the wrong way. Excuse me. But we can also place data based on location. Now, I talked about this key, and before the key was a simple thing. What if I basically created a compound key, which was the key for the table, and I encoded in that the country code for that particular dog? So country code of EU, US East, US West, right? I can actually use that key. And now the ranges are sorted by where data needs to live, because remember the sorting was all alphabetical, right? So now I know basically it's in alphabetical order and stuff needs to be placed on particular nodes. And so Cockroach is smart enough to understand that each node has a name, and I can actually tie a node to a particular location. And now ranges are written to a particular place. Now, this is such a critical piece of Cockroach. And this is one of the key ways in which we fought the speed of light, which is actually, you're never going to beat the speed of light. And that's why I always think, our ultimate competitor is the speed of light. Now, it's really cool because it actually allows you to deal with kind of jurisdictional control of data too. We're not going to solve GDPR, but we could definitely help you kind of avoid some of the big issues that you're going to have, right? By tying data to a location, right? And so there's some really interesting things you can do here, and a unique capability to Cockroach. And this is all done underneath the covers, and actually we're really simplifying the way you deal with this in a multi-region format in our next release. So stay tuned. We got some really cool stuff coming out. Now, Rebalancing replicas is really critical, right? So you want to shard your database, you want to add another server. What do? Well, I got to go rewrite my code base because it's just a nightmare. Sharding database, manual sharding is just an absolute nightmare. For us, we simply spin up a node, point it at the cluster, and Cockroach is smart enough to say, hey, let me rebalance this data because I got a bunch of empty space on this new node, and it's going to basically rebalance things, and now everything's good. I basically just sharded the database, right? You can do this very easily in Cockroach. And it simplifies the entire thing. Again, kind of a core principle about distribution of compute from a distributed point of view. But this movement is what's really, really important here. Now, we can also survive a failure. So if anybody's familiar with Kubernetes, another like a core concept, like built-in resilience. And so we can actually survive the permanent failure of a node. Let's say node 3 has gone down here. Well, we're smart enough. I forget what the timeout is. Maybe I forget what it is. I think the timeout is a couple minutes, but if a node goes down and it's just unavailable for a couple minutes, we don't do this right away because we don't want to rebalance all the time. Like if something just drops off for 10 milliseconds or, a minute or whatever. Like, so after 5 minutes, it'll say, hey, wait, I'm missing replicas, right? The Raft group understands it's missing one of its replica, right? And what it does, thank you, it's 5 minutes is the default. Somebody actually answered in the chat. And so after 5 minutes, it says, hey, look at the blue replica set says, hey, the leader says, hey, man, I'm missing one of my replicas. I got to create a copy of this somewhere. Great. The red leader said, I'm missing a copy, right? I got to create it. So Raft allows us to ensure we're always going to have 3 copies of that data. And that's why Raft is such a critical part of understanding how this works and a critical part of the way that you think about building your own distributed systems as well. And so that's really what allows us to do that. So it's pretty cool. We're just spin this up. Now, again, we can survive. Oh man, I keep going the wrong way. New keyboard, everybody, sorry. I can survive basically a small temporary failure, which is basically, leaseholder understands that one of its replicas is out of sorts and it makes sure that it's going to be up to sort. So it just says, hey, make all these changes so you're aligned with, the 2 other replicas in this replica set. And it takes care of that, right? When someone comes back online, right? So, all right, so that's the baseline. We did a little bit about storage. We talked about Raft. We talked about kind of how we distribute data. And I'm at, 35 minutes past. We're doing well. So the question was, how can we scale a database during high peak situation without saturating network bandwidth? Quick follow-up. Is there Cockroach's Kubernetes operator which supports auto scaling? Okay, so 2 questions there. How do you scale up without saturating network bandwidth? Well, do it like, take that into consideration. Don't add 15 nodes at once into your implementation, right? You're going to see this in the back end. Add a node at a time. Let the database rebalance. Add another node. Let the database rebalance. Add another node. I think work with our team to actually help you do that. We've worked with lots of organizations in sorting out how you intelligently scale. Is I think the first answer. And I think, Michael is on the phone. If you wanted to add a little more into chat on that, I'm happy. That's totally fine. But I think you got to think through those sort of things. But again, thank you for the question because it points out a really, really important point about distributed principles, right? Like if you're gonna basically start adding things to a cluster, you have to start thinking about the physical nature. What is this gonna mean to network bandwidth? So it is absolutely the right question to ask for distributed systems. Now, our operator currently does not support auto scaling in Kubernetes. I know that's something that we're working on. I can't promise dates because people would, be upset at me. But that's kind of one of these things. We do have people who are doing auto scaling in say, an Amazon in front of Cockroach and using load balancers and doing some interesting things in kind of more of a manual. But in the Kubernetes, our operator does not do auto scaling yet. Okay. I find that to be a really interesting day 2 operation that could be great for some people. So, but great question. Thank you. And I will try to continue to check those out. So how do transactions work, right? So in a distributed system, this is some really difficult stuff to take care of, right? So I've got a transaction that's happening in Sydney and the same record is being updated in New York at the same exact time. Who wins, right? Like people joke, I always say, who wins? That's difficult to deal with. And so we're doing that. We're using Raft. We've implemented serializable isolation in our database. So if you're not familiar with isolation levels, this basically is going to, lock out, basically stop any of the odd kind of eventually consistent issues that you're going to have with data. We've done this because we built a database for kind of relational, transactional workloads. And this is how we actually do it here in Cockroach. So let's take a simple distributed transaction. And I'm going to go through the case where this just works. I'm not going to go through the oddball cases, but there's a section in our documentation called the life of a transaction, which if you want a great read, again, Jesse and team do such a great job. Check that out. It really helped me understand this. But let's just insert two records into our dogs table. I'm going to insert Sunny and Ozzy. They aren't in there yet, right? And so, well, on the back end, if you understand kind of how relational databases are built, right, there's a SQL statement, but underneath that gets translated into a bunch of different transaction statements, right? There's always going to be at least three, right? Begin, something, and commit. Now I can ask any node, remember, right? I can lob a transaction into any single node in Cockroach. So the gateway there is just the gateway node. It's one of these four that are here on the screen, right? And so what happens is it finds the leaseholder for what I want to write. And so the leaseholder here is the red leaseholder. It says, hey man, I want to write this record. It creates this kind of temporary record in some special space that we have. It says, hey, hey man, I'm writing a transaction here to this range, so we gotta do this. It goes and finds its followers, the replica set. It's writing those. Those are temporarily written. One of the replicas returns back an acknowledgement. So I've got quorum. I've got two of these three have now written the first insert. Now the second step actually happens. Now I need to write Ozzy to the blue range. Same thing happens. It sends it out to the replicas. One of the replicas gives an acknowledgement back. I now have two of three. I have quorum, right? I have quorum across the red replica. I have quorum across the blue replica. I can now send acknowledgement back to the original requesting node and say, hey man, this thing's good. The transaction is going to go to commit. And now I can send back to the requester acknowledges. Now, that's a simple, straightforward, just work. Now, lots can go wrong here. We have implemented and worked on the transactional model of Cockroach for years. What kills you in building a database is all these crazy little corner cases and things that can go wrong. Now, in distributed systems, there's a whole lot of little weird odd balls that can happen throughout this whole process. So again, I would go check out some of our documentation. We go through some of these things, but I think for us, it's important that we've been through a lot of the strange corner cases of what can go wrong, right? All right, so now that's kind of the lightweight on transactions. Let's talk about now, SQL execution as well. So let's just see here. There's a question here. Is the default replica set 3 for Cockroach? And how do I think Michael might have already answered that. He's quick. You're quick to the draw, Michael. So is default replica set 3 for Cockroach database? And should the default number of nodes be 3? Okay, so great question, actually. So in Raft, you're going to have a replica, and so how many replicas you want, right? And so, yes, by default in Cockroach, we have 3 replicas of data. Now you can set that to 5 or 7. We see people go to 5. It really comes down to kind of what you want to survive and how many nodes you have and how fast you want data to be accessed in different regions you have. And it really comes down to the physical model of what you want to solve for. Now, by default, we're 3. And so that makes sense. Like, say I had, Cockroach and on 9 nodes across 3 regions. I'm going to set it up so I want, 3 replicas, and I'm going to direct copies of that data, 1 in west, 1 in central, and 1 in east, so that I can survive a regional failure. That's a topology that we actually implement in Cockroach. Now, in our next release, we're going to make it dead simple for you all to do that. Like, stay tuned here. Like, there's really, really interesting things going on. But what if I had 5 regions and I want to survive the region of any one, the failure of any one of those? Would I go to 5? Well, what are the probability? What if I had 8 regions and 3 in each, and I want to survive the failure of 2 regions? Well, it comes down to basically how you want to survive and what you want to optimize for. Is it speed of access? Is it resilience of a region or a node or rec? And that really comes down to personal preference and the SLAs and the requirements of your application. And I think our team does a lot of work working with customers to try to sort that out. Our sales engineers, our support team, our enterprise architects spend lots of time thinking through that, and really it depends on what you want to solve for. Now, the second half of the question is, should I always have 3 nodes if I have 3 replicas? Well, yeah, I would recommend 4 or more. That way you do have this redundancy. You do have, like, if something goes down for 5 minutes or 10 or 15 or 20, I'm still going to get quorum, right? Because I have 2 or 3 replicas, but I think in order to really optimize the value of the physical space and the physical value of something, or this distributed consensus, 3 or more it's definitely 3. It's 1 or 3, definitely not 2. But I would highly recommend something more than 3. I think Michael and the team can answer that in more detail. Yeah, so somebody actually just pointed out, they pointed in the QA. I hope you guys can see this. If not, Michael, can you just copy that link over into the chat so everybody can see it? We do have an interesting tool that allows you to basically say, hey, what do I want to survive? How many replicas do I need? All this stuff that Bram, one of the original members of our engineering team, actually built out. Really cool. And it actually helps you understand some of this stuff. So thank you, Michael, for getting that out there. Okay. All righty. So now execution. So I'll get right into the graphics of this. So distributed execution is something that's been part of my life. And the way that I originally understood this here at Cockroach is, I actually worked at a company called Hortonworks, and there was the Hadoop thing. And, I did understand MapReduce and how that works. And so if you think about this, kind of a little bit the same way that MapReduce works, but different in its implementation and kind of some of these things. But you can start there to actually get it. Say we wanted a count of, of customers by country from a table, right? From this customer table. Well, what we're going to do is we're going to ask any node for the count. And so I'm asking New York because that's where our office is. And so what's going to happen, it's going to push down this count to the other replicas and the other regions, right? And so I'm going to scan all the customers in one range, scan the customers in another range, scan the customers in the red range. And I'm going to pull all that together. And I'm going to do this group by country. And I'm going to do a count. And I'm going to do that on each of the nodes in each of the regions. And then I'm going to bring that all back to one place where I originally asked, right? That original gateway. And I'm going to return that back to the end user. So it's kind of like, let's map this out to all the places and bring it back. This is all part of this distributed SQL execution. Now, there is a whole lot of stuff going on here. And most notably is our build out of a cost-based optimizer. If you know a database, you know what a CBO is. The team here at Cockroach, led by Rebecca Taft, actually published a whole paper. We have a Sigmod paper that gets into a little bit of this and a lot of our architecture. Another great resource if you're looking to read a really good, interesting paper about an architecture of a distributed system. So I would go check out our Sigmod paper as well. But yeah, we built out a cost-based optimizer that's not doing just the traditional things that you would think in a legacy CBO. Taking this where data lives into the context of cost gets really interesting. And so we're doing some really interesting innovation on that side of things as well. And kind of, again, unique to this kind of distributed principles and distributed concepts, right? Location and physical nature of data and physical nature of compute becomes extremely important in distributed systems, and sometimes often difficult to deal with. So, all right, yeah, thank you. JP, I believe, just posted a link to the Sigmod paper as well. Hopefully that's valuable to you as well. It's a great paper. So then let's talk about latency. I've hit this up a little bit, a couple different spots here. But, okay, so when we used to build out apps, when I first started coding in the, whatever, decade or more ago, we built an application server, and then there was a database that ran on a server. And what we would do is you go out and figure out, like, okay, what's the size of my database this year? Go figure out the license cost, and then get the biggest damn server you can get to with your extra money to actually run that database. And that's how far you could scale, right? That was your vertical scale, was based on basically that thing, right? And so, but the latency here, well, the app server was sitting right next to the database server, or often it was on the same machine. Right. And so latency became, well, the speed of the motherboard, right? Or the speed of the bus, the bus, right? And so, but then, you had speed with the Ethernet, or maybe it was just latencies are no joke, because the speed of light is unavoidable. It is physics, y'all, right? It's a constant, right? And this comes into play when you start to have users all over the place, right? So if I'm logging in from San Francisco, I'm logging in New York, and I have my database in US East, well, I'm getting a 12 millisecond round time trip from my East Coast, but I'm getting 70 seconds from, let's say, my West Coast users. Now, this doesn't seem like a whole lot. 70 milliseconds seems kind of acceptable. In fact, there's this thing called the 100 millisecond rule that the original builders of Gmail thought of and actually validated. And they said, look, at anything under 100 milliseconds seems like real time to humans. Anything over, it seems like there's a delay. And I don't know about you, but I see a delay in an app now today, and it's like a delay of like 10 milliseconds. And I feel like, oh my God, 110 milliseconds. I'm like, oh my God, it's not working. Users are kind of sensitive to this. And I think we're all becoming more and more sensitive to this. But if you think about this as a 70 millisecond, round trip time, well, what if I'm doing multiple different things from the application to the database? I mean, this could actually quickly accelerate to 300, or, God forbid, a whole second back and forth, right? And so the speed of light actually becomes a really big thing, because actually we're having lots of different transactions, right? Now, we also had to deal with things like, outages, right? And so what we did also, we had a primary and a backup system, right? A primary and secondary, and we were doing this kind of async replication. Now, it's super expensive, difficult to maintain. The failover from primary to secondary actually becomes a problem. You have now new latency actually introduced to various different users. It's complex, it's costly. And so there's a new way of thinking about this. And actually with distributed systems, that's exactly what we're doing. Like for us, well, what we do is just like take this huge amount of money you're paying on this huge database, run it on this massive, huge server, and you're doing it on two places, and the secondary server isn't even being used, right? So you go from this active passive system to an all active system, and you intelligently deploy basically instances of your database. So you could be 3, you could be, like in this case, 5 different data centers, and you're doing this for a couple different reasons. We're going to come back to like the survival thing, but ultimately it's like, can I put the data closest to my user, right? And that's exactly what we allow you to do. And then we can actually tie data to particular locations based on where people are accessing it. So records for East Coast users, the leaseholder, that primary, is located in US East 4, right? The leaseholder, the main record for the Raft group, for those in Southern California are located in US West 2. And now I'm ensuring very, very low latency access to those users based on where they live. And now that's a unique capability of Cockroach, and allows us to get this kind of latency equality throughout the entire cluster. So my favorite people in Chicago, all the great White Sox fans, they can access, this US Central over in Iowa, right? So, but this is really cool too, because what if an entire data center goes down, right? US West goes down. Okay, great. I have replicas now that are in other places. And now I have this 7 milliseconds plus 24 milliseconds, because I was actually going up to US West and back, right? Like I actually get the same thing back and forth to US West, right? So we're actually dealing with this latency equality and outage all at once. And the trick here is to think physically and logically about your data, okay? Now, this seems all pretty difficult, but actually in configuration, it actually is pretty simple to do. What we're doing is we're partitioning tables based on how we name nodes. And what you see here at the bottom is partition by list. I want by locality. Locality and ID is actually locality field in the record, and the ID, that's our primary key for this table, right? And I'm taking all the values that are as in this partition, right, as US West 1, US West 2, into one set of servers, central into that one, right? And so I can basically now tell you to say West, Central, and East. And now, depending on where I want things to go, that's how I do this, right? And so I could do this, I could change this in real time, say I add, I can just alter partition, right? And so there's a really, really interesting things here. Now, Michael, thank you for noting on that. There is a dramatic simplification of this coming up in our next release. And I'm sorry to do that advertisement 3 times, but I've never been more excited about a feature set being released definitely in my almost 3 years, 2.5 years of being here, because we're going to take this all down into some really simple ways of thinking about what you want to survive and how fast you want to get data to users. But this is all pretty simple stuff to actually take care of, right? And it should be, right? We just want to make data and access to data is super easy and possible to get to, right? So, okay. So our last topic here, so this is pretty good. 7 pretty intense technical concepts. I'm going to get through all of them here today. That's good, right? So when you think about data, and when you think about latencies, and you think about where data lives and the speed of flight, well, we're dealing with transactional data. And if I want to get, sub 10 millisecond on all my transactions, that's tough to do when you have data living in Sydney and New York and London and Moscow and like all these different things. It's important when you have it across the United States. And so There's a lot of things we've done at the transactional record to actually do with this. We actually have lazy transactions. We're doing write pipelining. If you're familiar with pipelining from other different computer engineering concepts, it's also kind of similar. There's asynchronous writes. We're doing in-flight writes before commits. Let me just go through. I think it's the best way to actually go through it. So how do we actually do this with lazy and pipeline, right? So in the serial method, what you did is you basically did each piece of the transaction. Remember, a SQL statement got broken down into 4 pieces, and each transaction actually does it. And so the 2 bars are 2 machines, right? So basically begin, write, I'm going to write 2 records and commit. So I'm going to start this transaction. It goes pending. Okay, great. That comes back. I'm going to write Carl. That comes back. I'm going to write Nigel. That comes back. I'm going to actually do the commit. Okay, that comes back. So literally, I've now done 4 statements, and I have to wait the round trip time for each one of those to go back and forth, right? That's the serial method. Now, what we've done is we're actually doing something called lazy and pipeline. We're actually going to go and write Carl and Nigel. And so that's going to reduce that, collapse that down into 2, right? And then we're just going to do the commit. Now, what I've done is I've saved this amount of time. Basically, you basically can presume both are going to go and you're going to come back and the commit's going to come back and forth, right? And so we're pipelining in the first part, right? And being lazy about it. And we're taking care of this transaction. Now that's pretty cool. I've saved a fair amount of time in this transactional performance point of view, right? Big deal. Now we did something in the, oh man, Michael, I don't know what release that was. Was that in 19.2 we introduced parallel commits? But parallel commits is just some really cool engineering. And again, it's in the Sigma paper, but basically, look, we can't change the speed of light, but I can change the photons is basically the way I think about parallel commits. I can change what I'm going to actually send over. So I can actually say, hey, look, if I'm going to commit a record on here and I see around that record, all the data is correct, I can actually say, hey, look, here's a transaction. Here's all the data. Take a picture of this. If everything looks good, before you even do all this back and forth and all these things, just tell me, acknowledge, and it's going to go well because I know everything around this looks good. And we can be 5/9 sure that that's actually going to commit on the other node and come back. And I'm doing all these things kind of at once. Parallel commits, pretty badass, pretty awesome, right? And so I just explained through this. Let's just show it, right? So lazy, pipeline, and parallel is kind of some of the key stuff that we did. This is the last feature that came out in Cockroach that I was excited about. And I think the multi-region stuff is going to take it over, but this is pretty cool stuff, right? So again, with lazy and pipeline, right, we're doing Carl and Nigel at once, but we're actually sending over the transaction commit record for Carl, right? Where we're saying it's staging, right? Now all that stuff comes back. And what we're doing is we're basically doing this all at once and understanding that all these operations are complete. And we've now replaced this kind of the commit marker with one that's going to be distributed so that on each node, we actually know these things are going to happen. And so we've taken the time, which is saved here, which is the simple thing, and we saved even more. And allows us to do some things and to get past the speed of light and some of the bigger issues you're going to have in some really deep ways. And so I did not even start to do this justice. It would take me probably about a half hour to give a complete outline of exactly how this works. Again, it's in the Sigma paper. I wanted to give at least a high level understanding of like the way you think about things, the way you think about kind of how you package things up in a distributed system is important because of latency, right? What I'm doing in one place and how I have to get that done in another place. How do I package that up, send it over into its own atomic unit so that we can actually start to shrink the time things take? Because again, the speed of light is no joke, okay? And so that's kind of all the stuff, I think I hit everything here in Cockroach, right? I hit all these 7 topics. Now, somebody asked about Kubernetes. Yeah, we definitely deploy on Kubernetes. We actually a database that was built. It's a natural fit for a distributed orchestration platform like a Kubernetes. We have a lot of people using Cockroach on Nomad as well. Nomad, HashiCorp Nomad's also awesome. I find it to be a fantastic orchestration layer. But again, it's distributed system. There's a match in the way these things are actually dealing with things. Somebody asked about an operator. We definitely have an operator that's actually helping with day 2 operations. We're pretty simple and straightforward to run on Kubernetes because we were built for that, but definitely an operator. And then how to get started. We have Cockroach University. Actually, we just published a new course today. Forgive me, I should know exactly the name, but I just went through all this architecture stuff. go check out Cockroach University. Our team did a great job of relaunching and getting some new coursework out there. So go check that out today. But you know what? I think the best way to get familiar with Cockroach is go out and use it right now. And you know, to me, this is the world's most advanced database, and making it easy for people to consume. You know, we're going to actually manage all the back end to support the operations. Please do go check it out. And so, yeah, thank you in the chat, Michael and JP. Fundamentals for Java developers was just released today, so in Cockroach University. But go check out Cockroach Cloud, use Cockroach University, and thank you all for joining me today. You know, I appreciate the questions along the way. I hope Michael answered anything I wasn't able to answer. And again, I thank you for taking your time. I do hope this was valuable. I believe there is a survey at the end of this. Please do take the survey. It's important to us to make sure these things are useful and available to you. So, all right, everybody, thank you and have a great day.